Colligative properties are properties of solutions that are going to depend on how much solute you have in the solution, but not necessarily what type of solute is the one that you have. So the first one that I'm going over is the boiling point elevation. That's actually telling you what's happening to the boiling point of a solution versus the boiling point of a pure solvent. So when you have boiling point elevation, what that means is that the boiling point of a solution is going to be higher than the boiling point of the pure solvent that you have in that solution. So for example, if you have a solution of sodium chloride in water, that's just table salt, right? Um, the boiling point for that solution is going to be above 100 Celsius degrees. The boiling point for pure water is 100. That temperature is representing the temperature at which the water evaporates to become a gas. So what's happening is that when you have just your solvent, right, just the water, for the water to go from liquid to gas, the intermolecular forces that are acting, holding together the water molecules, they need to be broken. So the heat that is being added to the solution, that heat is being used to break apart the solvent-solvent interactions, okay? Or those interactions that you have between the water molecules. So when the temperature reaches the 100, then enough energy has been added to the water for your particles to escape the liquid state and become a gas. When you have a solution, now you have the solvent and the solute. So the amount of energy that is required to break all of the interactions apart is going to be greater because now in your solution you have solvent-solvent interactions, you have solute-solute interactions, and you have solvent-solute interactions. And all of those interactions, they need to be broken before the liquid becomes a gas. So that's why the boiling point of a solution is greater than the boiling point of the pure solvent. I'm going to use TB for boiling point. It's a boiling temperature. So that colligative property that I have listed here is telling you that the boiling point of a solution is always greater than the boiling point of the pure solvent, regardless of how many particles you have, regardless of what type of particles you have. If you have a solution, you will have more interactions, and the boiling point for that solution will always be greater than the boiling point of the pure solvent. So we have an equation that we can use to calculate the boiling point of a solution. The boiling point of the pure solvent is something that we can find on a table. That's a physical property of a substance, so it's something that we can just find. Now, in that equation, we have terms that we don't know what they are. We have the lowercase m, that one we already know. Its unit for concentration is the molality of the solution. Kb is the boiling point elevation constant, and that's also a numerical value that we can find on a table. It depends on the solvent that you have. And then the letter I is representing the number of particles that you have in a solution. The numerical value of I, right, or the number of particles that you have in a solution is going to depend on the type of solute that you have. Ionic versus covalent. So let's do the example so you get to see how to use this equation, okay? You should keep in mind, right, when you're doing your calculation that if you're calculating the boiling point of a solution, whatever number you're finding, it must be greater than the boiling point for the pure solvent. So in my example, the solvent is water, okay? So the boiling point for water, it's something that you probably know, but the information is there just in case. So you have that the solvent is water, the boiling point is 100 Celsius degrees, and whatever number we're calculating is going to be greater than that. Now let's check the other information that you have in the problem. The numerical value for the constant, it's also given. Okay? So you have that Kb is the boiling point elevation constant. We're going to have one value for this colligative property and then another one for the next one. The units for that constant is Celsius over molality. Okay? So the unit for concentration is going to be canceled out because you're multiplying that Kb by the molality of the solution. The concentration of the solution is also given. You have 3.60 molar, and then you have your solute, the formula right there. That's sucrose. Now, something that you need to know is how to identify a compound as ionic or covalent. In that formula, you have three nonmetals, carbon, hydrogen, and oxygen. Since you don't have a metal, there's no transfer of electrons. Okay? All of your nonmetals are forming covalent bonds. That compound is covalent. When you have a compound that is covalent, and it's a non-electrolyte. Okay? You do have covalent compounds that are electrolytes, and those are the acids. Okay? So in this case, you don't have an acid, it's just a covalent compound. When a covalent compound is soluble in water, the solubility is determined by the intermolecular forces that you have between the water and the compound that you're dissolving. But the compounds that are soluble are going to dissolve as a whole molecule versus an ionic compound. When an ionic compound dissolves in water, you're going to get all of the ions in solution. So the number of particles that I is going to depend on how many particles you're getting from every mole of the solute that you have in solution. When you're dissolving a covalent compound, the numerical value of I, it's always 1. every molecule remains in solution as a molecule. So your concentration is not affected by the number of particles because whatever number of moles you have, that's what you're going to get in solution. So when I'm doing my calculation here, since my solute is covalent, the numerical value of I is 1. So I have all of the numbers that I need to plug in into the equation to calculate that boiling point. I is going to be 1 because it's a covalent compound. So the molality is given. I'm just plugging in the numbers into the equation. So we already know, or we are already expecting to get a number that it's above 100. And you know you're going to get that because you have 0.512 times 3.60. Whatever number you're getting from that part is added to 100. So I'm rounding my number. I have 101.8432 from the calculator, so I'm just rounding that number to 3 significant digits. The molar concentration is given in 3 significant digits, so I'm going with that one. So 102 greater than 100, so that's actually what we are expecting. So let's go over this numerical value for I for a little bit. So the I in the equation is just telling you the number of particles, okay? Now I'm giving you an example here. I have CH3OH, which is methanol. It's a covalent compound. It is soluble in water. Every molecule of methanol that you're dissolving in water remains as a molecule. So if you have 100 molecules of methanol in water, you have 100 molecules. It's not breaking apart into anything else. The molality of the solution, right, is telling you the concentration of that compound in solution. So if the concentration of your solution is 3 mole, it means that you have 3 moles of methanol for every kilogram of solvent in that solution. And 3 moles of methanol is the same as all of those molecules in water. So the number is not increasing or is not changing because your molecule is not breaking apart into anything simpler. When you have ionic compounds like what you have on my second example, NaCl, sodium chloride, something very simple. In sodium chloride, you have the ion of sodium and the ion of chloride. The concentration of your ions in solution is different from the given concentration. If you have a label that says that the concentration is 2 mole, that's 2 moles of sodium chloride for every kilogram of solvent that you have. That's actually the concentration. But the number of particles is not going to be 2 moles because every mole of sodium chloride that dissolves in water is actually going to give you 2 ions. You have the ion of sodium and the ion of chloride. This here breaks apart into the 2 ions, Na plus 1 and Cl minus 1. So you're getting 2 ions for every mole of sodium chloride that you have in solution. The numerical value of I is telling you how many particles you're getting. So the numerical value of I for a compound like sodium chloride is going to be 2. So when you're looking at an ionic compound like iron oxide, the one that I have on the right side, you have the ions of iron and the ions of oxygen. They're combined to give you that compound iron oxide. The numerical value of I is telling you how many ions you have in every formula unit of that ionic compound. So I have Fe2, that's my subscript that's telling me that I have 2 ions of iron, and then I have my subscript for oxygen, which is 3. So that compound is composed of 2 ions of iron and 3 ions of oxygen. The total number of ions is going to be 5. That's the number of particles that you have. So for this compound, FeO3, the numerical value of I is going to be equal to 5. You have to take into consideration when you have ionic compounds containing polyatomic ions, okay? The polyatomic ions are bonded together by covalent bonds, so you cannot break a polyatomic ion into anything simpler. If you have the hydroxide, right? Let's say that you have NaOH. The polyatomic ion hydroxide remains as a unit. Okay? The bond that you have between the oxygen and the hydrogen is covalent, so you cannot break that bond apart. When this one breaks apart in solution, it's going to give you the ion of sodium, the ion of hydroxide, and the numerical value of I is equal to 2. You have just 2 particles for every formula unit, the sodium and the hydroxide. Okay? So it's very important that you review those polyatomic ions. So if you have sulfate SO4 with a charge of -2, you're not breaking apart the S and the oxygens. Okay? They're bonded together by covalent bonds. They will remain as a whole unit in solution. When you're comparing boiling points for solutions, look, your equation is telling you that the boiling point of a solution is equal to the number of particles times Kb times the molality plus the boiling point of the solvent. If the solvent is the same, right, in your different solutions, you will have the same Kb, you will have the same boiling point for the solvent. If you have the same concentration for all of the solutions, the molality is going to be the same, but that numerical value is going to depend on what quantity you have for the value of I. The greater the numerical value of I, the greater the boiling point of your solution. So if you're comparing a solution that is the concentration is 3 mole for, let's say, the methanol, right? The first one here. And then you have a solution that is 3 mole for the sodium chloride. The numerical value for the methanol for I is 1. But when you have sodium chloride, the numerical value for I is going to be 2. So when you do your math, your mathematical operations in that equation, and you don't have to actually do it, since you have more particles for that ionic compound when it dissolves in water, the molar concentration is the same, but the number of particles is twice as many for sodium chloride. So the boiling point for that solution is going to be higher than the boiling point for your solution containing the covalent compound because for the covalent compound, the numerical value for I is going to be 1.